now we have a matrix Q. And what do we know? We know that A0 is equal to this Q transpose A times Q. Okay? Or more importantly, what we should say is that A is equal to Q, I should say Hermitian transpose here. Let's leave ourselves a little bit of room. This should be just Q. This should be our first iterate. And then we will put Q Hermitian transpose right there. Okay? Now we start iterating. Okay? So we take this matrix A0 and we apply a first Givens rotation to it as part of our current step of our QR algorithm, or implicitly shifted QR algorithm. Okay? Now, to maintain this equality, we can't just put these two matrices in here, because now we have changed things. But what we can do is we can also plop in G0 here and G0 transpose here, because then this becomes the identity. Okay? The inverse of a Givens rotation is its transpose. And what that means is that as soon as we actually compute that Givens rotation, we can apply it to this matrix Q in order to go back to maintaining equality. Okay? And hopefully you see what I'm getting at. If during the implicitly shifted QR algorithm, every time we compute a Givens rotation, we also apply that Givens rotation to our matrix Q, then what we in fact are doing is we're accumulating all of these unitary matrices that come up during the execution of the implicitly shifted QR algorithm. Okay? Once we're completely done, okay, eventually we will have come up with some updated Q that has been hit by a whole bunch of Givens rotations, many from each iteration of the implicitly shifted QR algorithm, and then many from the fact that you do many such iterations. And the net effect of that is that you get that this matrix, which you have accumulated, times the final iterate that you get, let's call it AN, times that matrix transposed, Hermitian transposed, is actually equal to this matrix A. And what we have noticed is that, hey, that matrix actually converges to a diagonal matrix. So now what we have is that A is equal to some unitary matrix times a diagonal matrix times the Hermitian transpose of that unitary matrix. What we have done is we've computed the spectral decomposition. Okay. Now, what does it take to apply a Givens rotation to a matrix? Well, if you think about it, we have this matrix where we are accumulating the eigenvectors. We now apply some matrix that has a small Givens rotation somewhere in here. Let's see, let's call it gamma minus sigma, sigma gamma. The rest of this is just the identity. And what you notice is that this particular Givens rotation only affects the corresponding two columns in the matrix in which you're accumulating the eigenvectors. And then as soon as you have computed another Givens rotation, you apply that as well. Now the application of the Givens rotation to our actual tridiagonal matrix A is order 1 computation. It only takes a few computations. So the actual expense of each iteration of the implicitly shifted QR algorithm actually comes from applying that Givens rotation to the two columns, because that's an order m computation. Okay. Now, you end up doing about m such Givens rotation applications per iteration. Of course, with deflation, you lose some of that as the matrix gets smaller and smaller, but let's not get into that. So each iteration of the implicitly shifted QR algorithm is then order m squared computation. And the rule of thumb is that you need a few iterations per eigenvalue that you find. So you do some constant times m times order m computation to take your tridiagonal matrix A and make it into a diagonal matrix. So now what we have is a pre-process that costs order m cubed computation to make the matrix into a tridiagonal matrix, and then we have an order m cubed process that takes the tridiagonal matrix and makes it into a diagonal matrix. In the process, you compute all of the eigenvalues and you compute all of the eigenvectors, or approximations thereof, I should say.